Scalable mining of collective behaviors in social media using Riemannian geometry. Huan-Kai Peng
Yeah, thank you.
of Carnegie Mellon.
Right. Hello, my name is Huan-Kai Peng. Can anybody hear me well? Right, so my name is Huan-Kai Peng, and today I'm going to talk about angle shift, that's hash, scalable mining of collective behavior in social media. This is the work I have done with my advisor, Radu Matulescu. So the key term in this talk will be collective behavior, which is the high-level patterns of how people interact and spread information. And in the end, I will show you that understanding collective behavior is fundamentally important in understanding and engineering social media. So when I talk about collective behavior, I mean something that evolves dynamically over time when a piece of information is being spreaded on this social graph here. So for example, in t equals to 1, there are 3 green initiators who brings in this information from the outside world. And then at t equals to 2, there are 5 blue propagators who forward this information as is without adding their own opinions. And then at t equals to 3 to 5, there are 4 red commentators who forward this information but also add their own opinion about them. So if we want to have a high-level understanding of what's really going on, we can chart different statistics over time. For example, the number of different rows over time, or we can chart those graphical statistics, including the size of the largest connected component or the diameter of this evolving graph. And if we look at those plots right there, we can have a good understanding of what's going on, including what's the key rows in different point of time, or the fact that how the community saturates over time with the shrinking diameter. So with that information, if available, it makes it easier for you to either promote or suppress that information propagation. So that is why studying collective behavior is so useful. In previous works, however, what's being mostly studied is the usage dynamics, which is the number of usages over time. Identically, it's equivalent to aggregating the 3 colored lines in the left-hand side. However, there's an important limitation about using usage dynamics, which is if you only look at the right side, it's really hard for you to figure out what's really going on behind the scenes. In fact, in our previous work in 2013, we have shown that radically different collective behaviors can generate nearly identical usage dynamics. For example, one of them might be a viral news that spread like fire, whereas the other is a relatively contained kind of back and forth discussion. So mixing up the two is a serious issue because the action you have taken, if you know what's going on, will be very different. In one case, you might want it to spread broad and fast as possible, whereas in the other case, you want to really focus on that contained, focused group of people, right? So the takeaway message is that studying collective behavior is important for both understanding and engineering social media. So right now, the main question is, how do I identify all representative patterns of collective behavior given any social media? Like how many are there, or what are they? So here we propose our angle shift algorithm, and we will show that it is flexible, scalable, with a quality guarantee. To represent a collective behavior, we basically incorporate 2 kinds of features, time series and scalar. Time series features are meant to capture the shapes of important statistics, whereas the scalar features meant to capture the magnitude of important statistics. They are both used in many previous work, and incorporating both of them will ensure that our method of formulation is general and flexible. And just like our representation, a distance measure also consists of two parts. The first part uses that angle to characterize the difference in shape. So that's the angle of theta between two shape vectors. And for the second part, we use the conventional Euclidean distance between two magnitude vectors. And while this distance is geometrically intuitive, we'll show later that this simple distance can well recover the ground truths produced by human expert. And a good thing about this distance is that mathematically it's a matrix, which enable all kind of cool things like designing of our algorithm and deriving its quality guarantee. So according to our representation and distance measure, now every possible collective behavior lies in this specialized space M, which can be shown as the Riemannian manifold. And our task to identify representative pattern is just to find clusters in this specialized space. And one way to do it is to maximize the probabilistic density function over this Riemannian manifold. So it's a generalization of the famous mean shift to this Riemannian manifold that we define. So in this case, the density function will probably have two bumps around, or two hills around those two clusters. And what we do is essentially climbing up the hills to find the local maximizers, aka the true modes. So essentially we're trying to find a reliable and efficient estimation of those true modes. So what we can do is that we can iteratively take the gradient step and trying to maximize that density function. But here comes the problem, because we're now in a specialized space, and when we take a gradient step, that will give you a solution that's outside of the manifold, which is an invalid solution, and that's bad. So we need an exponential operator to map it back. So for the next iteration, we do the same thing. We take we take the gradient step, and we map it back. So essentially, our solution would travel along that red arc, and we'll show that it will converge to the blue star. And using tools from Riemannian geometry, we can derive all these closed form that is useful in our algorithm, and here it is. So the really good thing about our method is this nice guarantee. We can show that under very general conditions, meaning in almost all mixtures of distributions, our solution, the distance between our solution and its corresponding true mode can be bounded by something that converges strictly to zero. And in fact, it has two versions. In version 1, it says that for every solution x hat, there has to be a true mode that is nearby, meaning that every single solution is good, is recovering something that makes sense. In the second version, it says that for every true mode, there has to be a solution that's nearby. In other words, every true mode is identified. So to evaluate our method, we use a Turing data set, consists of 180 million tweets generated from a huge social graph. We extract 500,000 bursty keywords following a classic method. And for 100 of them, we asked 2 social scientists to provide human labels of collective behavior for us as the ground truth. So with that ground truth, we first evaluate that distance measure per set, excluding every influence from clustering algorithms. So what we use are those 4 distance measures. Besides the classic Euclidean distance at dynamic time warping, we also use the scale invariant distance proposed in the previous work, and also we extended, just to be fair, to consider both shape and magnitude features as I saw. So what we do is that for each of them, we just use the conventional hierarchical clustering and calculate the average mutual information, MI bar, between that label and the ground truth label, right? The higher the value is, the better the clustering result is. And we can see that the proposed distance measure and the SI star can better recover the ground truths generated by human expert. So now for those two winning distances, let's go ahead and compare their corresponding clustering algorithm. For our proposed distance measure, we use the angle shift, ASH. And for the SI star, we also extend the clustering method from the previous work as KSC star. For each of them, we use 10 runs of 10% randomly sampled keywords. And we calculate this statistic F, which is the ratio of within cluster distances over between cluster distances. A lower value of that statistic indicates a better clustering results. And in the table, we can see that our proposed method ASH not only give a lower average of that statistic, but a much lower standard deviation. That means that we can provide better result, and it's very reliable because every time you run it, it's consistently better. In terms of runtime, it's also much faster. It's about 50 times faster. And this is also consistent if we use the whole data set instead of the 10% data set. So now we know the advantage of our algorithm. We now use it to try to identify patterns in Twitter. So first, let's look at the right-hand side about the features that we use. Besides the ones that we have mentioned, we also distinguish whether a contributor or user contribute for the first time, or whether he's a recurring user, because a recurring user shows a much higher level of commitment, right? So let's look at the three patterns in the left. We can see a prominent peak for almost each cases, which is consistent with previous findings. And for these three patterns, we see that they're all dominated by the light blue line of first-time propagators. The only difference among those three patterns are the green lines. For example, for pattern 1 in the very left, it has almost no green line, but for pattern 3 in the right, it has a much more prominent green line. And we think we can explain that using the availability of internal versus external sources. For example, for pattern 1 in the left, there are a lot of sources from within Twitter. So example keywords include the Bloom Boy and Kanye Socks. And for pattern 3, on the other hand, it typically contains something that's ongoing, so the source is everywhere from television, from newspaper, right? So example keywords include NBA Final or Academy Award, right? And pattern 2, which usually correspond to news-related keywords, are somewhere in the middle, including keywords like Fawcett, Farrah Fawcett, and Madoff, Bernard Madoff. Our next two patterns are both dominated by the green line, indicating initiators. The difference between them is that in P4, in the left, there is a prominent community structure that emerges, indicated by the black and gray lines for size of largest connected component and graph diameter. And for pattern 4 in the left, it usually corresponds to keywords associated with anticipation. For example, WWDC and Christmas. For pattern 7, we see that the black and gray lines are completely flat, indicating a complete absence of community structure. And that is often associated with common emotion and advertisement. Example keywords include sad, oh my God, and free. Our last two patterns in Twitter are both dominated by recurring users. For pattern 5 in the left, it's a leader-follower kind of collective behavior, where example keywords include Iran election and Brazil Mrs. Jonah. And for patterns in the right side, it often corresponds to back and forth kind of discussion of people of common interest. Example keywords include online mom and the cookbook. Now I introduce two new applications that's enabled by knowing those collective behavior patterns. The first application is major event decomposition. When a major event happens, it also triggers a sequence of interrelated collective behaviors. For example, when Michael Jackson dies, at first, there's a rumor saying that Michael Jackson rushed to hospital following the first pattern P1 of endogenous mean, which means from internal sources. And later, we have this different red curve of pattern 2 because web media start to report it. And later, conventional media also start to report it using this pattern 3, and later they confirm that Michael Jackson has died. And that immediately triggered a huge wave of common emotion, saying rest in peace, sad, shock, and oh my God. And finally, a group of music lovers get together to talk back and forth about this tragedy and about the masterpieces of Michael Jackson. So from this, you can have a much deeper understanding of what's really going on behind the scene after a major event happens. And that's the underlying mechanism of how Twitter spread information. Our second application is clustering-assisted forecasting. Our basic assumption is that since all these collective behaviors are so different, maybe knowing which pattern they belong to can help us forecast the social dynamics associated with them. So here we build two models. Our baseline model is a single regressor where everything is treated as the same cluster. And our second model is an augmented one using one regressor per each cluster plus a classifier to tell which regressor to use. Now the result in the table shows that the augmented model, considering cluster information, can result in smaller mean squared error MSE, meaning that they can indeed produce better forecasting results if you know the clustering patterns. So for conclusion, we have presented angle shift, a clustering algorithm for collective behaviors. It is flexible in the sense that you can use any combination of features that has ever been discussed. It is fast, 50 times faster than the baseline, and it has a guaranteed solution quality. We use that to study collective behaviors patterns in Twitter and find the defining characteristic of those patterns. And finally, we have introduced two new applications which we believe there has to be more. And one of them is a more informative decomposition, and the other is a better forecasting. So thank you for your attention.